By the way, I think I can solve.
Hello.
Hi, how you doing? This we're off.
Hello. Sorry, I thought turned out I was muted.
No, I could hear you. I see Michael's joined as well.
Yeah, I saw Michael's joining. Kimberly's coming. Hi, Kimberly.
Hey, Chang.
Hi.
Hi. Did you see there was a message on Meetup for a Slack invite that just came through?
Okay, let me check. On you say Meetup?
It was, but I think Mike is on the phone. It's from, yeah, my Mike who's on the call.
Okay.
Sent it.
I didn't. Let me double check.
Yeah, he posted it on Meetup, so the email's on Meetup.
Oh, okay, saw it. Okay, gotcha. Mike. Let me add you, Mike. Let's I'll wait a couple minutes, but today John will be busy because it's yeah. Look. Hey, Mike, I added you to the Slack channel, and see if can you check your email to see if it has an invitation. John, I think John is very busy with the kind of like the election stuff. So today we are going to talk about the two kind of like puzzles that we saw last time. I've attempted a little bit, and what was because I can maybe share a little bit as well and see how it goes.
It'll be great. Yeah, I didn't get very far, and I didn't get to work on it today. I got pretty busy with work. So
let me see if I can pull it up in a bit. I'll start at 7:05.
So do you have the book that John's referring to, Counterfactuals, and I forget the blue book?
I just bought it on Amazon. I'll get it this week. I'll start like really read into it because I think like I was also like when I attempt to solve this programmatically, I start kind of like wondering, wait, why did I attempt this in the first place? And I think I start like I realized that I need more context.
Yeah.
And I had a discussion with one of my colleagues about kind of like A/B testing and like pre-post analysis of like, let's say you implement some sort of feature on a website. How do you actually measure the effect of the feature when you cannot, for example, A/B test? And I was like, okay, like this is like totally sounds like what we're trying to discuss here, but I realized I still cannot kind of like construct the causal graph to solve that problem from scratch. So I realized I have some like gap in my knowledge there. So I think I'm gonna start like really dig into the book.
Yeah, I was thinking of getting the book as well, but I couldn't quite tell. There are a few other books, and if anyone else had reviewed any of the other books.
Yeah. Okay, I'm gonna start. So let me wait. I thought where was John's presentations? I was literally I was. Oh, okay. Here we go. Here it is. So let me do a little intro here. Mike, I think you haven't been to our Causality Study Group before? Because I remember you from... Anyway, I'll just share the screen. Yeah, I think so. Okay, so let me do a little review of what we did last time. I'll just share a little bit of what I tried to do. Share screen. No, it's fine. Yeah, thanks for joining. So last time, John presented this slide, which you can find in the Slack chat. It's an updated Causality Study Group reference journal. So he has like a slide that is like, he calls it a journal of everything that we did. And so far we have been covering this thing called Degenerate State Block Causal Inference Python Part 2 about causal graphical models. And in here, let me open this. He has a Google Colab notebooks, and oh, here we go, slide meeting slides. And last time, what we were talking about was he was studying a book that he recommended, Counterfactual and Causal Inference by Morgan and Winship, that he wants to figure out the idea of backdoor adjustment. The idea of backdoor adjustment about like what, or in particular, I think we were at the point where he showed us two graphs. Sorry, I'm gonna go a little faster as a review, but there are two graphs of causal graphs. And let's say in this graph, by the way, if you please feel free to stop me. Can you see the screen, like the graph I'm showing here?
Yes, we can.
Yeah, so thank you. So in this graph, in both graphs, what we want to do is we have some relationships between some variables. And in both cases, we want to estimate the causal relationship between D to Y. So for example, the idea is that we have a variable D, which we think has an effect on our outcome Y. But there are other confounding variables in our model, and we want to isolate the effect of D on the variable Y. And so in this graph, if you look at the graph of how you can traverse, how you can like go from D to Y, there are three ways, right? You can go straight from D to Y. You can go from D to B to U to A. Wait, let me, oh yeah, that's right. You can go from D, B, U, A, V, F, Y. So you can take a long route to Y, or you can go from D to A to V to F to Y. So over here it says D, A, sorry, can you see my cursor? I'm like trying to move my cursor.
Yeah, I can, but I didn't remember why we could go in the opposite direction of the arrows.
Yeah, I think the idea was that like yeah, that was actually one of my questions as well. But I think, can I full screen this? Yeah. So what I was realized was that this graph is describing some sort of conditional probability model. So it doesn't really matter which kind of like which arrow it is. So it like in the sense that as long as there's a connection of like this, the how do you say, how you can go from D to Y is like a few ways that these variables get like mixed up together. So there are two ways that all those variables can get mixed up together from D to Y. The first way they get mixed up together is from DA, VFY. So you can see, oh, it's like A to D, V to A, however, but it's just like they have some sort of relationship here that can be kind of like factored as like probability. And the other one will be the long path from D, B, U, A, V, F, Y. And the idea is that, okay, so I want to isolate from D to Y, then I'd have to account for those two ways that can confound my analysis. I think that's what I got out of it.
Yeah, I think I see the first one. I still don't see the second one. But anyway, let's carry on.
Yeah, let me try again. So you go from D, and then to the left, you get the B, and
Right.
then left top, U.
Yeah, I understand.
Yeah.
But again, so let's see. From the first one, from D to A,
Mm-hmm.
that is because A is a confounder, and I think, sorry, not a confounder, it's a collider, I think they call it.
Yes.
So that's why I think I can see how, because if you know two of the variables and the A was held, the control variable, then you could deduce what V was, the impact of V. But I don't see why that's happening on the DBU.
Oh,
Because that
yeah,
is what they call the chain of the mediator.
yeah. I think it's, yeah. I don't know how to answer that question honestly, but I think I might have how do I say? I might have a explanation of what may be going on in a little bit.
Okay.
So we were at this slide, and then we were at the next slide, which is say, okay, there is something simpler. John was talking about descendants, about like blocking. Blocking is in the idea of that if we condition, let's say condition on this variable y t minus 2, by conditioning, we mean that we set it up as say, hey, if I don't know, if this person smokes or if this person doesn't smoke, we treat them as kind of like two separate data sets. And then we condition on the probability to calculate this. Then I'm like, okay, so like when I was like looking back, I'm like, okay, I'm still very confused. Basically, I didn't know like what exactly is going on. But I'll show in a little bit. But in this case, there are also two paths. You can go from D and then traverse this lower path from D to V to yt minus 2 to yt minus 1 and then to y. The other way is you go from D to V, again yt minus 2, and then you go up to U and then go to y. So there are two backdoor paths. And there are that's two ways of all those other variables can confound the effect of D going into Y.
All right.
And at the end, John presented this library where he used this library to draw a graph and then say, oh wait, like there's this thing called D-separation. D-separation, I look it up. The acronym D, or like this D stands for directional. So you can say some things are directionally independent by running some sort of a code. By running code using the library called causal model, or you build this thing called causal graphical model, and then you can draw it, and then you can decide which path are separated. And I think the question I threw out was, okay, so like, is being deseparated, does that, like, what's the relationship between this and the blocking of things that we're talking about here? So I was like, okay, like, I didn't know what that was, so I threw out that question 3 weeks ago. And then last week I was trying to study it, and I was like, okay, I'm still confused, but I think I have something I can share.
Great.
Yeah, so I was just gonna go ahead and share it. And please feel free to throw in a question. Because, for example, VREF asked, when you say, hey, like, so what does DVY, like, what does this mean? I think it's just a chain of multiplication of probabilities, but I don't know if that's true. I have to verify it. So I attempted, I will post this Jupyter notebook later, or put them into a Google Colab format. So what I did was, okay, I just took John's code and I did the same thing just to make sure I can get the same graph as him. But the idea is that we can build a causal graphical model with a bunch of nodes, and then we can specify what the edges. In this package, I think the edges are defined as Python tuples, as in, like, the first one is where you start, and then the second one is where you end. So if you see the edge here, I said season to rain. It means it will draw a season into rain in this case. And what this causal graph means actually is it represents some sort of a probability distribution. So you can see that this graph, I believe this is what it is. This is my guess. Is that it's trying to say that P of last thing slippery equal to this thing. Oh, I need to run. Yeah, I think I'm good. Hi, Xing Xing. Why is it not running? Oh, here we go. Hello.
Hey.
Yeah, sorry, I already started. I was trying to go back for a little review of what we did last time about the two graphs.
Yeah,
And
wonderful.
we want
Sorry.
to, yeah, we want to look into what deseparated means. So I went ahead and started. I don't know if you want to share later.
Yeah, go ahead.
Yeah.
Yeah, I will catch up later. Thank you.
So I tried to I copied John's code, and the first thing I was okay, let me try to build a model, just make sure I can run his code. And I think VREF said about he asked a question about what this graph means, like what those paths, they say d v y t minus 2 u y, what does that mean? Or like what this lower triangle or the bigger shape means. I think it just represents something like this. So every single causal graph essentially represents a relationship between the variables, and I actually don't know if it's like this or like season or maybe something like that, but I know it's like trying to represent some sort of probability distribution. This is questionable. I don't know. I don't actually know. So maybe I'm wrong. So please correct me if you know exactly, like I'm wrong. But I know, like, when you multiply these, you should probably get one of the variable. And so my guess is slippery. And the idea of conditioning is that we want to take out some of those things to make this easier for calculation or based on the data that we have. Sometimes we cannot calculate some of the condition probability here, but once we make some assumptions, we can take them out of the equation or do something to get that. That is one part I still don't know how to do it on data. So that's what I attempt to try next time. But and any comments before I go into the puzzle?
No, sounds good so far. Thank you.
Yeah, so I went into so actually I only went into one of the puzzle that I say, hey, like, so what's going on? And I took this puzzle too. So I have all those variables, and we want to estimate from D into Y. So my first question was, all right, can I build this graph? So I just say, okay, I have all the nodes and I define all the edges. Can I get this graph? And so I got the graph over here. I will post this Jupyter notebook later, but you can see I'm able to represent it as some sort of a probability distribution. And then I do have the graph here. D goes into Y, and the first path is D to V to YT minus 2, YT minus 1 into Y. And the second one is the one that goes through this collider, D, V, YT minus 2, U, and then Y. And this package that John gave us, or John found, has a way to calculate D separation. So my first question, okay, so what is D separation? I don't really know. So because I don't know, I'm like, okay, let me try a few things, like see what happens. The first thing I try was like, okay, if I don't do anything, is like, if I don't condition on any of the variables based on this graph, are U and V deseparated? So I just run it. Are U and V separated? And the answer is yes. I don't know if there's a way for me to, maybe do this. Oh, here we go. This may be easier. Okay, so my first question is, are U and V, the top two, are they unconditional independent? This is what the wording that John used. I think what he meant was that if we condition on nothing, if we don't say, hey, let's condition nothing on these two deseparated, the answer is yes. And then the next question, I was like, okay, so because this thing YT minus 2 is a collider, if I condition on it, I think like at the time, I was like, okay, this should be the same as unblocking. If I condition on variable, that means this thing is like non-existent on this probability distribution. Then U should not be independent to V anymore if I condition on YT minus 2. So I say, all right, let me set my first set of variable to be U, second to be V. If I condition on YT minus 2, are they still independent? And the answer is false. And then I just like try a few weird things. It's like, okay, like what about U to D when there's nothing? So if I want to go from D to U, I have to go through a collider, like going backwards, like D to V to Y, or I guess both ways. You can go from D to Y to U as well. Both ways you have to go through some sort of collider because Y acts as a collider as well. So I say, okay, if I go from D to U, unconditional on, not conditioning on anything, it should be deseparated. They should be deseparated. So I was like, okay, is that true? And I run it, and turned out yes, D and U are separated. So, and if I run, actually, let me run all this thing because I just realized that it may be nice to. So if I go from U, yeah, well, I just realized they flipped this time run it, flipped the picture. Okay, try again. So D to U, because they go through either way, D to Y to U or D to V to YT minus 2U. These two acts as colliders. So they should be separated, D and U, when I condition on nothing. So when I condition on nothing, D and U are separated. But if I condition on the collider itself, YT minus 2, it should also be, is it still separated? The answer is, whoops, no. Now if I condition if I kind of like condition it as in like, say, hey, this thing has to be fixed, then now D and U are unblocked. Now they're correlated or not independent anymore. And I was, sorry, any comment on this before I try the next thing?
No, I think that piece is, yeah, I understand.
So like, I think last time John mentioned the thing is like, hey, you act like if you were to condition or when, okay, I think this is a good way to say it is condition on a variable means you want to hold it fixed. You want to fix the value of this thing and just kind of take it out of your analysis. And what happens if I fix the descendant of a collider, in this case, yt minus 1? Like, I know that if I condition on yt minus 2, it will remove the block between u and v, or d and u. What if I condition on the descendant of yt minus 2, which is yt minus 1? What does it do? Let's try it. I actually don't know.
I think it will do the same.
I think it should do the same. That's my guess. Let's try. So if I go from U to D, okay, I guess we both guess that it should be no. So let's, I don't know, let's try it. Yeah, that's true. So, sorry. It's true that if I condition on its descendant, D and U becomes unblocked. Now they're deconnected. They're not deseparated anymore. And I think the same thing happens if I condition on Y. Y is like a second degree descendant of yt minus 2. Or I guess if you look at this way, D and U, they are, Y acts as a collider if you go from D to Y to U. So I think D and U, if you don't care about anything, I think if I do this, go from U to D and condition on Y, it should also give me a no. This is my guess. I don't know. I actually have not tried this.
Yeah, what I think is like when you do the white, so I think if I go back, so on the collider, when you condition on yt minus 2,
Mhm.
as I was trying to say, is what I was reading is you can basically think of it that that's you holding that constant. So basically, if you know two of the edges or two of the paths, you can always deduce the third one.
Yes. Yes.
And so, and then also, if you like, if you condition on a child, somewhere a child, not immediate, then basically that same thing's happening basically because you're conditioning on that child, it basically propagates and yeah, the weight of it may change, but you still basically, yeah.
Yeah, I think that's I was talking, I realized kind of like what you said. I think what happens is when I hold yt minus 1 constant, if I hold this middle or this child of yt minus 2, this thing constant, then yeah, okay. If I hold this thing constant, then it should mean that no matter what I do to yt minus 2, yt minus 2 basically has no way of, I don't know what it means. If I hold this constant, is this the same thing as holding this constant?
I think there's some leakage from it, yes.
Yeah. Okay.
That's what I'm guessing. I don't know.
Yeah, I don't know either. So I'm curious now. But I guess like if you think about, I was thinking about why, if you look at this whole thing here, I guess Y is a descendant of everybody, right? So if I hold Y constant, then everything should be correlated to each other, or everything should be dependent on each other, I guess.
Yes, let's try that.
What if I do this? U and V, like the topmost variables, and I hold Y constant. Yeah, so now they're also correlated.
Yeah.
What about this? If I hold D constant and then U and V,
That'll no, because if you hold D constant, you still have the collider there, and you haven't held white T.
Okay. Yes.
So it should be true.
Okay. The meeting will end in 10 minutes.
Oh.
I will just restart the meeting if it ends. So please just join on the same link. This will be Y, X, Y, and Z. All right, let's try it. I don't know. But Vera says should be yes.
Not true here.
Yes, you're right. And so I think I got this far. Like after I do a few of those, I was like, I got to this point, I'm like confused because I realized, okay, now I know how the kind of like a better understanding of blocking and how can I do this programmatically. I realize I still don't know how to estimate with D into Y. Like, what does that mean in terms of equations? So I look into a little bit of a block, and then I look into the degenerate state block part 2. What or this one? This link here. So I think what I don't know yet, but I think what John might say in here is next time is in the blog post it says, okay, this is a way for you to analyze how the backdoor argument of which one's blocking what, how they're separated works, but it does not tell you the effect, the analytical or like numeric effect of D into Y. You still need to do that calculation with data. So I think that may be where we're going next time. But this is a way for you to understand, okay, if I want to hold something constant, does it make sense? Because now I have a way to programmatically check things. I think with this, we should be able to check all the edges, or like, let the computer figure out how many ways I can go from D to Y. So if I say, hey, I go from D to Y, there are only 3 ways. And I can just do the same thing to say, hey, which variables can I actually block without unblocking the bad things? So because if I hold YT minus 1 constant, it will actually unblock this collider. So it's a bad thing. But I don't know how do I actually use this when in terms of probability calculation. I still don't know. That's why I decided to go ahead and order the book.
Yeah, I've ordered the book as well.
Yeah, but that's actually all I have. I did not attempt this because I think I got what I wanted out of trying on this graph. So I actually did not attempt this, and I'm like a little confused about how do I actually do this probability here. So I'm trying to understand that. That's all I have.
Oh, that's great. Thanks.
Thank you, Cheng.
Yeah. Yeah. So I guess my next question, I'll just post in the Slack channel. My follow-up question is like, and which variables we shouldn't touch to unblock. Yeah, I think the answer is yes, but I have not coded the way to do this yet. I think there should be some. If I just try every single path, I should be able to do that. But I don't know. Follow up to is like, how do I use this information? This is my question for myself. I still don't know. And there is a blog post here that I found. I don't know if it seems like John probably has something similar in his slides, but so I looked into this blog post. I didn't know what this person was talking about. I couldn't understand what he was trying to say. Yeah, that's all I have. I don't have anything else. Like, I guess we'll just we can just go back to the Slack channel and discuss there.
Mm.
Yeah.
Great, thank you.
Yeah. Any other thoughts or comments before I end the meeting?
No, thanks.
Yeah, it's actually very interesting, but I got too many tasks at my hand, so I haven't got a chance to look at it. But appreciate your input here. It's pretty great.
Yeah, thanks. I really wanted to look into it after I had a discussion with my colleague about how to A/B test something that you don't have information about. So in this case, it's like we want to estimate the effect of SEO on a website. Like you can change your keywords and stuff and affect how Google ranks your website. But the thing is, you don't have that data. You don't know how much Google, like you basically have no way to A/B test your, like if I change some stuff on your website, like how effective is that? You cannot do a traditional A/B testing on that, but maybe there's something you can do a cost analysis. I haven't figured out how to do that yet. Yeah. So I'm trying to understand a little more, like, can I construct a simulated data set to understand how can I use this package better? That's my personal next goal.
That's great. Yeah. So you think this causal analysis would be a good alternative way to solve some issue instead of using traditional A/B testing, right?
Yes, because there are actually scenarios even on websites that you can make changes that cannot be A/B tested.
Oh, yep.
Yeah, so that's my where I kind of like, okay, I really need to study this, but yeah, that's all I have. I will post this notebook to a Colab notebook shortly.
Great.
All
Thank
right.
you.
Thank you.
Yeah, thank you. Oh yeah, I saw Mike's message. I will share the link. I will share the link later. All right. Thanks, Mike. Thanks, Vera, Xinxin, and
Thanks, Jen.
Kimberly. I'll talk to you later.
Thank you,
Thank you.
everyone.
Yeah.
I'm sorry was late because of my puppy. So sorry about that. But it's a great section. Thank you so much, Cheng
No
and
worries.
Viraf.
Thank
Have a
you.
good evening. Bye.
Thank you. Bye.
Bye.